will be an interesting experience.
Well, there is always first time. Well, for me, it's really a pleasure to introduce Paul Hagelstein. Uh, Paul is a member of the Associated Department Chair at Professor of Mathematics at Baylor University. He got his BA at Rice University and got his PhD at University of Chicago, here, very close to us, with Bob Pfefferman, right? And he is
Yes, yeah.
a well-known specialist in harmonic analysis. So the floor is yours, Paul. Thank you for accepting my invitation.
Yes. Again, thank you for the invitation, and I've known Wilfredo again for over 25 years, I believe, and he's a great person to know in mathematics. I'm always interested to see what he's talking about. I'm looking forward to hearing he's giving a special lecture at the upcoming conference in Fargo when he has 50 minutes, so we got plenty of time to know what he's learning about, at Fargo, which is good. So I'm going to be talking about a very classical area of mathematics, the theory of differentiation of integrals. And I'm going to keep certainly a lot of the talk on a relatively low level for any undergraduates in the audience. And this theory begins with the fundamental theorem of calculus. So let's review an analog of a version of it. So let f be a continuous function of the real numbers. We define capital F of x as the integral from 0 to x of f of t dt. Then f prime of x equals little f of x. And so I remember in graduate school, Saunders McLean said that every talk needed a proof. So here's my proof. So hopefully I won't mess this up here. This is the proof of the fundamental theorem of calculus. So capital F prime of x is, by the definition of the derivative that we teach our freshmen, the limit as h tends to 0 of f of x plus h minus f of x over h. By the linearity of the integral, that's the limit as h tends to 0 of 1 over h of the integral from x to x plus h of f. And since f is continuous, we realize that limit is going to go to f of x. So we're definitely using the continuity of f. Now, most people don't really think about the fundamental theorem of calculus this way, but under the hood, it's really a result about the limit of averages of a function. We're basically saying that for any continuous function at a point x, the limit of the averages of f over small integrals shrinking toward x tends to f of x itself. Now, there are analogs of this in the Lebesgue I should mention that I was curious, at one point he's going to talk in Bilbao about this, and I was wondering, so who is the first person to articulate the fundamental theorem of calculus? And many people attribute it to Isaac Barrow, who's the first Lucasian professor, a predecessor of Newton. He is buried at Westminster Abbey, which is, of course, fully appropriate for the mathematician who starts the theory of differentiation of integrals. And he published it in his lectures on geometry. There's his name, Isaac Barrow. It's written in Latin. This is somewhat interesting. So basically, historians of mathematics consider section these two sections here, the section 11 to be the first articulation here of the fundamental theorem of calculus. And his drawing for this is not really what we'd expect. There's figures 109 and 110. And at this time period, a common publishing practice was just to cram all the diagrams onto one page. So it'd be easier for the typesetting. And so here it is. So this is diagram 109 and 110, and you can kind of see like these notions of tangent curves and all that. But basically, I can have a totally separate colloquium talk on this. But these figures 109 and 110 encapsulate their version for the fundamental theorem of calculus. So this is not like the diagrams I draw when I teach our Math 101 or 121 at Baylor, but that's how he treated the fundamental theorem of calculus. Now, the first, like a modern version of this that we would teach in measure theory is the classical Lebesgue differentiation theorem. And this says for functions in L1 of Rn, for almost every x, the limit of the averages of f over balls centered at x, shrinking toward x, tends to f of x. Now, this is an almost everywhere result. It's not true everywhere because you might have a function with some sort of like discontinuity. So it's not going to be true everywhere, but it's true almost everywhere that we get this result. I'm going to say a few words about a proof of this theorem. And so, underlining the Lebesgue differentiation theorem, there's a covering result that we call the Vitali covering lemma. It tells us the following. So let's suppose we have a finite collection of balls, open balls in Rn. Then we can find a subcollection of balls satisfying two things. One, the balls are pairwise disjoint. And two, that the ones we select fill up a certain proportion of the original class. Namely, the measure of the union of the balls that we select fill up, let's say, a constant 3 to the minus n times the measure of the union of the original collection of balls. So this is the Vitali covering lemma. Now, closely related as well is this what I'm going to call the centered Hardy-Littlewood maximal operator. And so this is an operator, MHL of C, C for centered. MHLC f of x is the supremum of the averages of the absolute value of f over balls centered at x. So you take the super of the averages. And there's a theorem, it's easy to show using the Vitali covering lemma, that the measure of the set in Rn where the centered maximum operator of f is greater than alpha is controlled by the L1 norm of f times 3 to the n over alpha. This is actually quite interesting. So this operator is not bounded on L1, but it's close to that. It's what in harmonic analysis we refer to a weak 1-1 inequality. So if you take any function f, I guess just Chebyshev's inequality, the measure set where f is greater than alpha is controlled by the L1 norm of f divided by alpha. That's true for all functions. And so this is saying that the Hardy-Littlewood maximum operator is sending f into something that's satisfied by all L1 functions, namely this weak L1 result. And we call this a weak type 1-1 inequality. And this, I don't know if there's any, aside from Wilfredo, if there's any analyst in the audience, but we use this type of result all the time. So our operators generally are not going to be bounded on L1. That rarely happens. The interesting operators, but we have this replacement, which is called a weak 1-1 inequality. And from this, you can play certain games to prove the Lebesgue differentiation theorem. So what we have here then is a paradigm. It's very interesting that from a covering lemma, like the Vitali covering lemma, we can get a weak type bound on a maximal operator. And from that, we can get a differentiation theorem, like the Lebesgue differentiation theorem. And in terms of like the history of mathematics, this is very interesting. The first person to really figure this out would be Norbert Wiener. A nice paper in Duke. It's called On the Ergodic Theorem, where he basically showed how you go from the weak type bound of a maximal operator to differentiation result. And from that, he was basically, well, let's say you have a measure preserving transformation T. You might have the, so you might take maximal ergodic averages. You might call that operator T star. He was able to show that T star satisfies a weak type 1-1 estimate, and from that get to the Birkhoff ergodic theorem. So it's a little bit more efficient proof of the Birkhoff ergodic theorem, which is quite interesting. And he showed that basically using weak type inequalities, the same techniques that would give us the Lebesgue differentiation theorem were the techniques that would give us the Birkhoff ergodic theorem. And it's not a surprise then that a lot of analysts, harmonic analysts, also like work in ergodic theory. One of your like colleagues at DePaul University, like Roger Jones, for example, some of you may know him. He's since retired, but or gone emeritus, but he did a lot of work in harmonic analysis as well as ergodic theory. He was, you've seen him at the Calvin Seminar in Chicago. Many of you know Roger Jones, so he was kind of sitting that interface between harmonic analysis and ergodic theory. This being a colloquium talk, I would say there's a really interesting book called I Am a Mathematician by Norbert Wiener. Quite interesting, actually. And he talked about and so I had got the book published by MIT Press. I was very curious what he was doing around 1939. And it's really depressing reading because basically he was hanging out in like New Hampshire at his cabin. And then he talked about his summer projects. And he basically did two things in physics he was very interested in, and then he thought he wanted to clean up the ergodic theorem a little bit. So he and a couple other people basically knocked out this paper. So for him, this gets third mention over the summer. For me, this would be a career achievement, basically, to make this kind of connection here. And for Wiener, it's something he just happened to incidentally do over the summer, the third, like in August, in like 1938 or something like that. Um, so some of you may know, like Paul Hamilton's book, I Want to Be a Mathematician, but Norbert Wiener said, I am a mathematician. So I do recommend that. Um, in some respects, though, you can go backwards. And so one of my favorite papers, maybe my very favorite paper by Eli Stein was a paper, analyst paper in 1961 on limits of sequence of operators, where something in there he showed how you could go from a differentiation result back to a weak type bound of a maximal operator. And so he was showing that there was an action implication going backwards. And then uh, Robert Pfefferman and Antonio Cordoba were able to show in certain cases you could go from the weak type bound on a maximum operator back to a covering limit. For example, if an operator is bound on an LP or weak type PP for P bigger than one, we have an equivalence between these. And I would say that, and it's primarily to Wilfredo I'm talking about here, that I'm going to say I've spent the last year thinking about how to go backwards here. If you have, let's say, some sort of Orlitz condition on an operator, a little bit more general than an LP bound, where you can go backwards. And so my student Block and I have been spending a lot of time thinking about that. And Block will probably say some things about that in the Fargo conference coming up. So this is still being fleshed out to what extent you can go backwards to going from the weak type bound of the maximum operator to show you have to have an associated covering lemma. Now, what about averages with respect to rectangles? Um, so the Vitali covering limit does not hold for rectangles. And so an example would be the Bohr staircase, named after Harold Bohr, um, which basically I could take, let's say, n rectangles all the same size parallel to the axis, and they all touch the origin. Well, if I want to take a disjoint collection of rectangles, I can only pick one out. But you'll notice in this case that, well, if I pick one of them out, it's only filling up roughly 1 over n proportion of the whole collection of rectangles. So it's interesting. There's this, I think Harold Bohr is slandered by conjecture, the so-called Bohr conjecture that any collection of rectangles size parallel to the axis, you could find one of them that would fill up a sort of proportion of the original. This is like obviously false. So I feel like Harold Bohr could not have really thought about this problem. I would say, incidentally, for the soccer fans, if you're a soccer fan, raise your hand, so I can see any soccer fans in the audience. Wilfredo. So interesting that Harold Bohr was a member of the Olympic team who has the world record for the most goals in a game and the largest defeat in the game. He played on the Danish or the Denmark Olympic team, and so he's not only good at mathematics, Harold Bohr, but was an accomplished soccer player. So this is a interesting observation here, I guess. Well, okay. So if you think about the paradigm, though, the covering lemma breaks down. So all of a sudden you begin to think, uh-oh, now we're not going to have a weak type bound here. We're not going to have a differentiation theorem. The kind of our world's going to fall apart. And it does. It can in a very spectacular way. So here's a result from about 100 years old now. It goes back to Nikodym and Boozman and Feller. That if you let F be the family of all let's say rectangles in R2, then there exists a function F that's an L infinity of R2 such that you don't have on any set of positive measure the averages of F over rectangles shrinking to X tending to F of X. So it completely breaks down. There's no good estimate you have on this. That's instantly reflected. I'm not going to get into this, but there's a result associated to Charles Pfefferman winning the Fields Medal that if you look at the multiplier of the unit ball in R2, that's the associated. So in other words, let's say I define operator by TF. The Fourier transform of T of F of X is equal to the characteristic function of the unit ball times the Fourier transform of F. That multiplier operator is only bounded on L2. And if you look at that proof, he was exploiting the problems associated to this type of collection. And so multiplier operator, if you have the multiplier is trivially bounded on L2, but you get nothing else. And so that's interesting how this manifests itself in harmonic analysis. There is some positive results, almost about 100 years old. So this theorem goes back to Jessen Marcinkiewicz, and I guess one of your, like a former colleague at Chicago here, Anthony Zygmunt, that if F's an LP for P greater than 1, in fact, I'll get more particular. If you can integrate F times the log of F to the n minus 1, then you do get um, uh, uh, averages of F over rectangles whose sides are parallel to the coordinate axes, tending to F of X almost everywhere. And so this is what we call the strong maximum operator, rather than where we average over balls. And we're not averaging over all possible rectangles, but just rectangles whose sides are parallel to the coordinate axes. There's some structure there you can exploit. And so you do get an analog of the Lebesgue differentiation theorem, not for functions in L1, but for functions in LP for P greater than 1, or functions you can integrate the function times the log of the function to the n minus 1 power. Well, Fredo, you may find this to be interesting in terms of the weak type inequality in this case here. We don't have a weak 1, we have this. The measure, so the strong maximum operators were taking averages over sides parallel to the axes of averages of F over sides parallel to the coordinate axes. That's a so-called strong maximum operator. So the measure set where ms of F is greater than alpha is controlled not by F over alpha, but F over alpha times the log of a constant plus F over alpha. And it's really interesting. Some of you may know Alex Stoklos. He pointed out to me that this result is not in the paper of Jessen, Marcinkiewicz, and Zygmunt. In fact, the earliest inequality like this I can find goes back to 1972, surprisingly late. Now, Zygmunt and Stein must have known this in the early 60s, I would think, but they never wrote it down. So Fava was the first person to articulate this. But you also got to think that Jessen, Marcinkiewicz, and Zygmunt proved this using iteration techniques, but this is 4 years before Norbert Wiener. They weren't thinking in terms of weak type inequalities. And so they just didn't work in those terms. So it's a little bit interesting. Some of these papers pre-1939 are difficult to read. And I kind of find it interesting. Norbert Wiener has a reputation of being hard to follow, but if you actually look at his Duke 1939 paper, it is surprisingly modern and clear to read, especially in the context comparing it to papers written before 1939. They are really tough to follow. And so anyway, but there is a weak type inequality for the maximum operator associated to sides parallel to the axes. This is the form that it takes. So this is a nice positive result. I want to say that the techniques of this, though, are essentially iterating one-dimensional techniques at this point. Now, I want to talk a little bit more generally now. Let beta be a collection, open-bounded sets that covers Rn. We have the associated maximum operator now, M beta F, which is M beta F of X is supremum of X and R, which is a set inside of beta. The averages of F over R. So beta might be the collection of all balls, all rectangle sides parallel to the axes. You could basically just pick virtually any collection you want of open bounded sets. You could talk about the associated maximal operator. You might wonder when it has a covering condition, and this is a really nice result due to Antonio Cordova and Robert Pfefferman. Pfefferman did this as a graduate student, actually working with Stein at Princeton, and Cordova was, I believe, was an assistant professor at Princeton at the time. And so they proved the following. So let P be finite, and let's suppose that the maximum operator satisfies. Okay, I see your pictures here. Do you see like the P up above right here? Like, I'm just curious what I. Okay, I see like a screen with photos of people's faces. It's kind of covering up the edge of my screen, but fine. I know there's a P up in here. So suppose the measure set where M beta F is greater than alpha is controlled by a constant times the LP norm of F over alpha to the P power. We call that a weak PP bound. And so this will be the type of estimate satisfied for any function that's in LP, basically by copying the proof that, Chebyshev's inequality. This is true if and only if there's two constants, C1 and C2, satisfying the following. So this is about to be the replacement of the Vitali covering theorem in this context. given a collection RJ in our collection beta, there's a subcollection satisfying two things. One, the measure of the union of the sets in that subcollection fills up a certain proportion of the measure of the original. Two, you can control the LP prime, to say Helder conjugate, like 1 over P plus 1 over P prime is 1, norm of the sum of the characteristic functions of the RJ tildes by a constant times the measure of the union of RJs to the 1 over P prime. And so this basically tells you you're given an original collection, you're going to a sub-collection that fills up a certain proportion of the original collection, yet you have to have some restriction on the overlaps, and that restriction is associated to controlling the LP prime norm of the sum of the characteristic functions of the chosen objects. I will remark that this relates, well, let me talk about the Bohr staircase for a moment. So the Bohr staircase could be a situation where, let's say I were given this collection of rectangles. Pfeffer and Cordova noticed that you really do have control over, let's say, where there's infield overlap geometrically, and that gives you certain quantitative information that you can exploit, and that should appear when getting a nicer differentiation result, like at least in terms of LP classes. So that's what they're exploiting in this case. So, for example, if you had the regular Bohr staircase like this, they just simply choose all the rectangles and recognize that using distribution estimates that you can control the LP norm, the sum of the characteristic functions of all the rectangles chosen. Blame it on L infinity, but they're an LP for every finite P. So the strong maximum operator then is bounded on LP for all P greater than 1. They could exploit that. I do want to say this is something I've been spending a lot of time thinking about. Conspicuously absent in this proof is, or notice that we have the P greater than 1. When P equals 1, one direction is very obvious. Namely, that if I can go, they have the Vitali covering theorem, right? If I know I can go to a subcollection that fills up a certain proportion of the original, well, P is 1, P prime is infinity, so I can, having an L infinity condition on the sum of the characteristic functions of RJ tildes basically means there's finite overlap with the RJ tildes. From that, it's very easy to show a weak 1-1 estimate. The question is, if you have a weak 1-1 estimate, what can you say about the covering result and so here's the problem. Suppose P is a weak type 1-1. You have a weak type 1-1 estimate in beta. Do there exist little c and capital C such that given a collection RJ and beta, there's a subcollection that fills up a certain proportion of the original and such that you can control the L infinity norm of the overlap? And I will say now that this has been one of my favorite problems for probably over now 25 years. I think now I know how to do this problem, actually. And so it's not obvious a solution, but that may be published pretty soon or submitted, put on the archive. And Blanca may talk about that in about 6 weeks. I don't want to steal her thunder, but I think now there's been some ideas regarding how to solve this problem. So I've mentioned this problem quite a few colloquium talks, and now this is like the first time I've mentioned this problem. I think I actually know how to solve the problem, but that's a totally separate colloquium talk that goes in very unusual, unexpected directions on how you handle something like this. Okay. Now, one thing really nice about the Cordova-Pfefferman result, though, is it gives us a way of controlling maximum operators associated to collections for which you cannot in an obvious way controlled by, let's say, a finite iteration of one parameter results. And so a good example of something like that would be like the Lacunary maximum operator. So let's suppose we have the set of rectangles, let's say in the plane, but they're oriented in a direction of the form 2 to the minus j. So let's say rectangles, the slopes could be 1/2, 1/4, 1/8, 1/16, and so on. You're not going to control this by one parameter estimates. That's simply not going to happen with infinite many directions. But they provided a mechanism for trying to control this geometrically, and they have the following result. So we'll let the Lacunary maximum operator be the supremum of the averages of the absolute value of f over what we call Lacunary rectangles. One of these rectangles that are oriented in a like a direction like 2 to the minus j. They were able to show by covering result that this maximum operator was bounded on LP for p greater than 2. Now, later on, Nagelstein and Steve Wenger were able to show using three analytic techniques and like orthogonality arguments is a very clever argument that, in fact, this maximum operator will be bounded on LP for P greater than one. I want to say over a year of my life has been spent on maybe a year and a half trying to directly prove this by covering results. Um, is weird. You would think that you could actually mimic, like you could go to the sub collection, or like, given a collection of Lacanier rectangles, you could go to sub collection, you could get some sort of LP prime control over it. People have tried, everyone's tried has failed to do this. Robert Pfefferman told me that he and Cordova were too stupid to be able to do this. I spent a year of my life trying to do this. I know Yanis Parissis, some of you know him. Well, Fredo, you might, he spent a lot of time trying to do this. It's kind of one of those lion traps you can kind of get into that looks like a problem you should be able to solve in a couple of days, and like it just kind of collapses on you. And you can get really frustrated. Now,
But the proof, the original
we
proof
know it's true.
between two
That's a
and
weird thing. And this is the really frustrating thing about it as well. The Cordova-Pfefferman result is an if and only if result. So in fact, we know there is the subcovering that works. But in terms of actually directly being able to generate it, we've never been able to figure out how to make it work. That's a little interesting about it. We know the result will be true, but we cannot actually explicitly construct the covering, which is strange, I'll say. We know we're going to win. In fact, there's even certain algorithms, we're going to win on the algorithm. But like, if you don't want to, let's say, unload the Nagelstein-Wenger theorem on it, how you directly handle it, we don't know how to do that. You might wonder, why would we care? The reason why we might care is that we think the best result might be something around like L log squared L. That if you have there'll be some type of Fava result where you can control the set where the Lacanier maximum operator acting on F controlled by alpha. It might be controlled by the L log squared norm of F over alpha. And Yanis Parissis and I decided to look at there's a certain bootstrapping argument that Nagelstein and Wenger used to prove this, and their LP bounds blow up extremely rapidly as P goes to one. And so, like, really, really fast. And so Yanis Parissis and I decided to sort through the arithmetic and realized, well, we could get like, it would bound like L log L to the 27th power or something like that. We think it's L log L squared. And so whenever the bootstrap argument is being used, you start really losing information if you're trying to get estimates on spaces between L1 and LP for P greater than 1. That's lost. Whereas a covering mechanism might actually preserve you more information. That's why you might care about that. Okay, so now this is generalized by Jogren and Jolene, who showed if omega is an n-Lacanier set, and so I don't want to really dig into the weeds on what this means, but let's say one Lacanier is something like 1/2, 1/4, 1/8, 1/16, something like that. Two Lacanier, you might have a Lacanier sequence. Lacanier sequence is being attached to any point in a one Lacanier sequence. And so let's say I could take, let's say, the set of points of the form 2 to the minus k. That would be one Lacanier. But let's say I said 2 to the minus k plus 2 to the minus L. Let's say that would be a 2 Lacanier sequence. And I could get more technical about it in terms of successor constants and all that. I won't go into that. If you're interested, I'd read like the Jogren and Julian paper itself. But basically, they said if it's an n-Lacanier set, then the maximum operator is going to be associated. So omega is an n-Lacanier set of n0, 1. You have beta omega being the set of rectangles in R2 oriented in one of these directions. Then the maximum operator is going to be bound in LP for finite P. A very interesting problem is, how do you define n-Lacaniarity like in higher dimensions? And this is a complicated thing, actually. So Javier Persay and Keith Rogers have a very nice American Journal of Mathematics paper where they have a notion of higher Lacaniarity, like in 3 or more dimensions. Malabika Permanic and our student Edward Kroc have an analog as well of higher Lacaniarity. They don't agree with each other. This is a case where people in the area don't really quite have a clear notion of what the right definition should be. Like, how do you want to think about Lacaniarity in higher dimensions? In particular, how do you characterize an interesting question. The set of directions, let's say in 3 dimensions, for which the associated directional maximum operator is bound in LP. And so that's a very interesting question. I'll be saying a few more words about that later. Even in 2 dimensions, this is unsolved in general. But in some respects, I would say this represents the world record in terms of the worst maximum operator that we can come up with for which we have some sort of nice control over what's happening. Um, so I want to talk about a result due to Michael Bateman. He's a student at Nets Cats in Indiana when he came up with this result. Uh, there's a yellow star on this, meaning that this result is very close to being correct, but it's not exactly quite right the way it's being phrased here. Um, so omega is a set of directions in 0, 1. Then Bateman had the associated directional maximum operators bound on LP for all p greater than 1, if and only if omega can be covered by finitely many inline sets. So Bateman was basically saying in 2 dimensions that yes, the Jogren-Jolene result is sharp. Basically, this is the collection for which you would get LP bounds in the maximum operator for p greater than 1, and it's an all or nothing. It's either the maximum operator is going to be bounded on all p greater than 1, LP for all p greater than 1, or none of them. It's an all or nothing situation because this is for all the values of p at once. It's if and only if. Again, no higher dimensional analog of this result is known, although there's been progress made on this by Malabika or Permanic and her student Edward Kroc. I will say that there was and I'll get to this time permitting, there was a certain type of directions that Bateman did not consider in his paper that the status is actually unknown. And so this is something that my student Blanca Rodillo Murguia, as part of her, basically, I asked my student to extend the Bateman result to higher dimensions. And I didn't realize I was giving my students such a hard problem at the time. And it turned out we were really trying to understand the Bateman result, and we realized there's this exceptional set of directions that we found that kind of escapes the easy there's problems with one particular set of directions that are not included in the Bateman theorem. So that's why there's this yellow star here. I'll try to say a little bit more about that later. Now, so we might consider what is like the weakest condition that might be interesting for a basis. And so let's say we take a collection of open bounded sets in Rn. It's almost like if you're watching this and you were kind of zoning out for a while, it's almost like you can re-enter the Colloquium talk at this point, like just reset here. But this will relate to what I've talked about before, but it's almost like a reintroduction here. So let's say we have a collection of open bounded sets. It's a density basis if you have for any set E, if you like, the averages of the characteristic function of E over sets in the basis shrinking to X tend to the characteristic function of E of X almost every X. And so I'll repeat that. It's a density basis if for every measurable set E, you think of your favorite measurable set, for almost every X, if I look at the averages of chi E over arbitrary sets in beta shrinking toward X, they will tend to chi E of X. So we'll have that condition. That's good. So this is kind of the weakest condition on a basis that we would think to be reasonable. Now, a really nice result is the following. We're going to let C beta alpha be the soup over sets of finite measure of the measure set for the maximum operator acting on chi-E greater than alpha divided by the measure of E itself. So Boozman and Feller showed that if beta is a homothetic invariant basis, meaning it's invariant under translations and dilations. So, for example, balls, I translate a ball in the plane, I get another ball. I dilate it, I get a ball. A rectangle, I translate it, I get a rectangle. I dilate it, I get a rectangle. So basically, we're not looking at some really goofy set where it's almost like a totally random. There's no connection between how the basis elements relate. So basically, this is a very natural condition to put on things. Then beta is a density basis if and only if C beta alpha is finite for every alpha greater than 0. Well, Fred, something I find to be kind of puzzling about this is that, sure, let's say we had a weak type estimate on the maximum operator. Let's say weak 1, well, fine. This thing would be bounded by uniformly, like this condition here. A weak PP bound, that's fine. We would get things that are nice. But this is for fixing alpha. And so you could have these C beta alphas, maybe not behave like 1 over alpha or 1 over alpha P. They could behave like e to the e to the e to the e to the 1 over alpha. And fine, if it's satisfied, it's a density basis. So they're not requiring any control over how rapidly C beta of alpha can grow as alpha goes to 0. But if it's finite, you're looking at a density basis. Um, I'll say a few words now about Boozman and Feller. Feller is very interesting, William Feller, and he's probably, uh, about, you can turn off the microphone. When you see the name Feller, what do you think? Anyone? Anyone can say something here. Does the name Feller resonate with anybody by chance in the audience?
Probability books.
Yeah, so here's William Feller, and here's the book. You may have a copy of this on your shelf. So, so he's probably best known for this book. Great book, actually. I kind of like I like that book. I was just teaching a course in as Allen and Spencer's book on the probabilistic method, and he got into some really detailed estimates. And I thought, oh man, how do I prove these things? And this book helped me out a lot in carving through certain detailed estimates. Yeah, so this is William Feller, and so he's best known in probability. And then we have um, so here's kind of a nice trivia question. Who are the 4 people in this picture? So like if can anyone identify anyone in this picture? Okay, so we have Finchel, and then Alexandrov. This is going to be Herbert Boozman and Bjorn Jessen. Interesting. I've always wondered. I've asked many people, like, can anyone identify this photograph in the background? And so finally, I decided to check, and thought I want to see just how good AI is. So I inputted the image into AI, and I learned that this photograph was actually taken at Obervolvox. So I need to actually now contact the people in Obervolvox saying, all right, I need to know what is this photograph because in my colloquium talks I show this picture and I don't know what this picture is. I don't think it's a Solvay conference because I've looked at all the Solvay conference pictures and this doesn't match up, but it's some sort of math conference and I'd really like to know what that is. Does anyone by chance recognize this? It's kind of hard to tell because of the glare. Does anyone recognize this picture by chance? Okay, so I'll need to contact the Obervolvox people about this. Anyway, Herbert Boozman, he was a professor at the University of Southern California for a good while. And what's interesting is he retired at 70. It might have been a mandatory retirement based on the time period. And then he went into art. And so this is, he has some really great paintings here. He liked to, like the hard edge school, and some of these are like acrylic on masonite or oil on masonite. And so anyway, so these are Herbert Boozman paintings here. I think this is really cool, actually. Every so often they come up for like auction or something like that. You can still find them in Los Angeles galleries. They're very interesting. So, so here leads to now what uh, um, sometimes for job candidates, this is maybe I guess we have a department chair here. I frequently ask our job candidates if they were going to win a Fields Medal, what would it be for? Like, do they know what the theorem is going to be? They kind of give me the strange expression, when I ask this question, but it's kind of like you can learn a lot about someone by asking this question. So this is kind of for me a holy grail problem, maybe the most important problem in the field of differentiation of integrals, and it is at least over 50 years old, and it doesn't seem to be, it's resisting all attempts to handle it. The halo conjecture. Let beta be a homothéty invariant density basis, and suppose it satisfies what we call a weak, what Stein would call a weak type phi estimate. The measure set for m beta acting on the characteristic function of a set is controlled by the integral of phi of chi over alpha. Now, in terms of Tauberian conditions, that means C beta of alpha is controlled by phi of 1 over alpha. You might think of phi as being your favorite convex increasing function. De Guzman wants it not to be too goofy, so phi of t equals t for small t. That's fine. But you might be thinking the real action is when alpha is getting small. This could be growing very fast.
Sorry,
But the Hale
Paul,
conjecture is
what,
then that the
Paul,
measure of the set, yes.
where is the C in the inequality? It's missing.
Just a constant here.
No, but
It might depend on
you say
10 or like on phi itself, but there's some constant here. Yeah,
no, but you say that the phi weak phi the constant is less than phi. Where is that C sub B constant in the statement?
So is there a question about this inequality?
Where is this CB?
Oh,
C sub B
CB,
alpha. They
this.
right.
So that
Oh,
measures the Tauberian, like how big it is, that the measure is set. Uh, I mean, you could even ignore that. I was rephrasing the halo condition in terms of C beta of alpha, but that's what this would be, right? So basically,
C better. Okay.
you're asking a
Yes.
good question. So while we're thinking about C beta alpha, it's kind of like a measure of if you're given a set E, where the maximum operator acting on chi is going to be greater than alpha, we kind of think it'd be something kind of enveloping E, if you like, and we're basically measuring how much bigger is that envelope to E itself. So it might be a C beta 1/2 is 7. We might have that maximum operator act on a characteristic function of E, but where that maximum operator is greater than 7 or 1/7, let's say it might be something, or 1/2 is maybe some set size 7 times that of the measure of E itself. So it kind of gives us a gauge on how bad the maximum operator is. So that's the C beta of alpha. And so anyway, but you could even ignore the C beta alpha. I rephrased it, but you could just read this inequality directly if you wanted to. Well, the conjecture is you can replace that characteristic function of E by a function F, and the same inequality holds across the board. Just everywhere you see a chi E, replace it by an F. Now, normally bells should be ringing in the head that this is a major problem. There's absolutely no way this should be true. One reason why is we're looking at weak type inequalities, and this is a very important thing. Uh, the space weak L1 is not a Banach space. So there's no triangle inequality. So the weak L1 norm of F, you might think as being the supremum of alpha times the measure set where F is greater than alpha. So let's say we take this function here, 1 over x. Let's say the weak L1 norm of that is 1. So in other words, if I take my alpha, the alpha times the measure set where f is greater than alpha, that's going to be 1. By symmetry, restricting from 0 to 1, if I take f2 of x is 1 over 1 minus x, that has a weak L1 norm 1. But if I add these together, that weak L1 norm is 4. Everywhere that function is equal to 4. Like if you look at where x is 1/2, you're going to get 2 plus 2 is 4. So basically, I just took two functions together, a weak L1 norm 1. I added them up, and now I have weak L1 norm 4. And in fact, the more functions you have, the worse it gets. So, like I tell my students, you think of analysis like you break down, synthesis you put together. A lot of analysis, we may have a function, we want to decompose it into pieces, ask them operate on the pieces, and then put things back together again. Um, that worked in a lot of context. And for this particular problem, they're going to get in trouble because let's say I have my function, I decompose it into, let's say, sums of uh, simple functions or whatever. I act the maximal operator on those individual pieces. I get certain weak type estimates. When I come back to put things back together again, I lose because I don't have a triangle inequality. And so that is a problem. And so your normal guess on why this should be true would be false. However, we're not just looking at any operator, are we? We're looking at a maximal operator, and so these behave and associated to a homothétian invariant density basis. So it's not just any maximal operator. I'll remark this is kind of curious, but if you actually did a centered basis, like the center maximal operator, where wasn't homothétian invariant. So M beta has a so this is I'm probably talking to just Wilfredo on this, but it's a very interesting technical point. M beta is a maximal operator. I take X and I'm taking beta is a collection, and I'm looking at the averages over any set of beta that contains X. As opposed, so let's say the uncentered Hardy-Loaded maximum operator, I might take a point, I might take all the balls that contain that point, not just the balls centered at that point. If I looked at a centered maximal operator, right, my collection beta associated to beta of x, so for any x, I'm only allowed to average over the set and beta associated to x. You can satisfy this estimate, but not this. So it's weird. The Boozman-Feller condition on the maximum operator is actually extremely important. Like it's a weird thing. Another thing I find to be really interesting about this question is that like I read once one thing I like about the iPhone now in ways like is if I want to take a picture of something to remember something, I can do it. But I once read, I think it's somewhere in the University of Chicago library, someone said that harmonic analysis is the study of translation invariant operators. Um, uh, Probably someone from Russia, I'm guessing. I think Coven, maybe someone like that. I wish I could find that quote, but there's a lot to that quote. That's because, like, what is harmonic analysis? And people think Fourier series and all that. I said, no, it's a study of translation invariant operators. And um, so what's interesting about this is you have a translation variant structure in there. So all of a sudden, you're trying to go from a weak type inequality. You cannot use a triangle inequality. What is your friend to this? What is helping you out? Well, you know the maximum operator has a translation invariant structure. So, and not only that, it has homothency invariant structure, meaning this thing is invariant under dilations as well. So all of a sudden, you're trying to go from a uh, like if I'm thinking of a restricted weak type inequality to a full weak type inequality. And generally, you should not be able to get away with this because you don't have a triangle inequality, but you're trying to rescue the situation by exploiting two things. One, you're dealing with as we call it, Boozman-Feller basis. The way in beta is defined, combined with this translation variance, combined with dilation variance. So you're imposing two separate algebraic structures on the operator as well. So this is not just any operator you're working with. So this is one reason why this is a really fascinating problem, actually. And so I'm now in the mid-50s. I'm getting very pessimistic that this problem will be solved in my lifetime. I hate to say it, but it's kind of like there might be a counterexample, but in terms of a proof, like it's really unclear how this works together. But one thing I love about this problem is you're really looking at some very basic fundamental concepts: translation, dilation, weak type estimates, and this Boozman-Feller condition. And so it's kind of like the ingredients are all very, very simple, but how you put them together is extremely complicated, actually, on a problem like this. So anyway, I love this conjecture. Let's see. I need to finish up really fast, don't I, here? How much time do I have left, Wilfredo? Should I be done like in a minute or so?
You can take 5 more minutes or so. We start
Okay. So I will
2:05.
say that as some positive results on this here. Well, de Guzman showed that if the halo conjecture were true, then for any homothency invariant density basis, the maximum operator would have to be bounded on LP for sufficiently large P. De Guzman is someone I wish I'd have met. I never met him. He passed away before, like at the time I was in grad school. Wilfredo, you may have met him. I never actually. Did you ever meet him, Wilfredo?
Yes, I met him a couple of
Okay.
times.
People I wish I'd have met would be Zygmunt and de Guzman. And so, anyway, and I find this to be a little interesting. And in some respects, this is a reason why you might think the halo conjecture should be false, because I can imagine some sort of maximum operator that might be bounded on something, let's say, like the exponential class, or something that's like sitting between L infinity and the LP space of finite P, uh, but not on LP. Now, one thing that's really annoying about this is I don't know of any proofs that something is a density basis without going through a weak type estimate, in particular a weak PP estimate. So even showing it's a density basis is going to be a problem. Yeah, we have this condition on C beta alpha, but whenever I've actually needed to know that, I've always known something a lot more, namely something like a weak type estimate. So this is kind of deceptive, this result. That makes me think it'd be false. Well, Alex Stock last night, at one point, thought, well, we're going to disprove the halo conjecture by constructing a homothetic invariant density basis that would not be bounded in LP for any finite p. And then and then something unexpected happened. We proved the following. So let's suppose you have a homothetic invariant density basis of convex sets in Rn. We proved automatically it's bound in LP for a sufficiently large p. We can prove that, and that was really exploiting the Calder-Sigma decomposition, and quite interesting. The estimates we got quantitative estimates for LP, like the LP would be necessary in terms of, let's say, the C beta of 1/2. And I'll mention that if you're in terms of weighted norm inequalities, there's a so-called Fuji-Wilson constant um, that abstractly is something as an A infinity, and we know it lies that A infinity is formally the union of the AP classes, but we were able, using this estimate here, to go from if we knew that Fuji-Wilson A infinity constant, to place it in a particular AP class, and that constant P is sharp. We got, but based on the result of Hatton and Perez. So this has consequences outside of just differentiation of intervals. But we can only what was irritating about this, though, we felt like this should be true for all p greater than 1. And we had a little breakthrough occur in 2022 in 2 dimensions that it would hold for all p greater than 1 if we had a density basis condition. I'm going to put a little yellow star on this because we were relying on the result alluded to by Bateman, and there is that special case of directions that created a problem for Bateman we discovered after the fact also actually sits in this. So there's this weird set of directions we don't know how to control. Like, you have to really go out of your way to construct it. It's not a natural thing. And most people never run into this set of directions, basically. But it's a little bitty little fly in the ointment, which is unfortunate here. We discovered after the fact. And it's one of those things where if there's a mistake in a paper that's 20 years old, it kind of can percolate through the literature, like it creates some headaches, basically, that it's we're doing the best we can. So anyway, to sort that out. And I would say that we have pretty good insights on how to do this in higher dimensions. And I feel fortunate that my student, Blanca Radil McGee, she's just got a postdoc now at University of British Columbia. She's going to graduate this year, and she's going to be working with Isabella Laba and Malavika Pramanik. And essentially, we have very good ideas on how to do this in higher dimensions based on Malavika Pramanik's work. So she's about to go into the place where that's in their wheelhouse. So I expect good things to be happening. It's kind of like we have a very good idea how this is going to work, but there's kind of be a very technical 40, 50 page paper probably coming out of this, but we kind of have the big picture of how this is happening, modulo these exceptional sets of objects. So I think that's a good place to stop. So I guess I'll take any questions, and it's been fun discussing this.
Well, let's thank the speaker first. Thank you very much for your talk. I have this result with Stokolos, where has been published?
Indiana, the Indiana Math Journal.
Oh,
Yes.
Indiana.
Yeah, a couple of years ago. Yes. And I would say this is really good news, but the counterexample, like this is almost like the countering it's the yellow star thing. The analogs of that, we started having to do harmonic analysis on trees and sticky maps, and it got really, really complicated. Like the kind of sets that we get into, like this kind of gets out there, basically. I'm just skimming all of this for time permitting, but basically the result involving the yellow star has been accepted. In fact, was just published in the last 2 weeks. We got 2 papers, one in Duke and one in Revista. And so this got really technical, very interesting, actually. I strongly suspect, due to the referee comments, that like either Nets Katz was a referee or Javier Perse or Malavika Pramanik, and so basically Bateman made an extremely subtle error in a percolation argument. Like it's the beautiful paper, and like one line, there's a little problem. And Blanc and I were working, and we just, sometimes things just don't really quite sit right. Like something's not quite right. It took us forever to figure out what the problem was. Like 2 years, basically. And but we have now a pretty good idea of a slight subtle issue in terms of a percolation argument that Bateman was using. And it only occurs in a very particular case, which I can see why Bateman did not see it and the referees did not see it. I'm highly sympathetic. Uh, but um, but Bateman's argument works for Cantor sets, normal Akinari sets, a wide variety of things. But there's a certain kind of implicit separation condition he wanted to have, and if you don't have that, there's some issues. And so this result with Alex was Stoklos was published in Indiana, and then there's two follow-up papers in Duke and Revista. Yeah.
Any other question or comment?
Yes.
Yeah. So
Melanie.
a lot of these theorems seem to really be so incredibly rigid that they're really fixed in Rn. Do any of them extend if you had a something kind of like maybe R2 with a little bit of wiggliness? You know how
Yes.
like if you're
They
tiling
they
a
they do.
floor and
Yes.
wiggle it a
Uh,
little.
Good question. And so, in fact, one of my a paper, I'm doing a paper blocking out with Fedya Nazarov, I should say, and he wants to do things on general measure spaces. So I'm so used to working on RN, but he wants to do everything on measure space. Frequently, a condition that we're going to want to have is a so-called doubling condition, where let's say we have a metric space, or let's say we're given separability in some condition like that, but we may have let's say we have a metric, we have a notion of a ball, right? A lot of times we want to, when we dilate the ball by constant two, we want to control the measure of the dilate, let's say twofold dilated ball by the original measure of the ball. If you have that, then that lets you do the Vitali covering game and a lot of the games you want to play. If you lose that, things can be weird. And a lot of times the rules simply won't even be true. It's like there's a huge, shift. But with that, you can do virtually all these theorems. There will be a context whether or not the underlining measure has some type of doubling condition. Yeah. And then we have the whole theory of weighted norm inequality. So like the maximum operators being bound on LP of W. Normally we want to have W, like some sort of doubling conditions to be satisfied to get virtually anything that we want. But yeah, you're right. We can make these. A lot of things people like Stein refers to doing things with certain manifolds. But normally you want to have some sort of local compactness and some sort of doubling condition on the metric, and then you're pretty well good to go. Yeah. Yes.
Thanks.
The 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 condition of that the convex is the sets are convex is crucial, right?
For
It
our
was
argument, it is correct. Yes. And why is it crucial? It is because um, let's say that um, let's say we have a convex set that we can basically place a convex set inside a rectangle where it fills up a certain proportion of the original rectangle. There's a so-called Fritz-John limit that lets you do that. And then what happened is we ended up doing like a cauldron. This is about to get very technical, but a cauldron-Zygmunt decomposition based on, let's say, particular rectangles. In other words, and homothétie is important because let's say we have a rectangle of a certain eccentricity. We want to divide it up into, let's say, 2 to the n subrectangles, but we do not want to leave the basis. And so the idea is that you may have your blob, you're placing inside a rectangle, but then you can do a Cauldron-Zygmunt decomposition based on those rectangles. And so that mechanically was very helpful for us. Yeah. Now, what is a little bit interesting about the halo conjecture, though, is my suspicion is this is going to be true for convex bases, but one could come up with an exotic non-convex basis, maybe lacking a regularity condition for which this breaks down. But we have very little experience working. I mean, I can give you some bases right now. I could write down. Let's say I looked at the bases associated to all homotheses of, let's say you're constructing the Cantor set and you get these, those, we start cutting pieces out and you're getting like these, like you're approaching the Cantor set from the outside, basically. These lack of regularity in the sense that if you put it in engulfing a ball, these fill up a very small proportion of the original ball. Or let's say my bases were fat Cantor sets, and I decided to take all homotheses of it. Yeah, take your favorite fat Cantor set, and you look at all homotheses of it. That's your basis. Is it a density basis? I have no idea because And so it's all like it's kind of like we can start writing down bases. But showing it is a density basis is hard. Showing a basis that maximum operator is not bound on LP is relatively easy. Showing as a density basis is hard. Like, I don't know if you ever thought about the problem. I'll just fine. Let's say you take your favorite fat Cantor set, positive measure, and now you're going to take your favorite Lebesgue measurable set, but you're going to look at supremum of averages of that set over uh, like Cantor sets shrinking toward that. It's a little bit weird what that's going to look like in terms of like kind of the structure of what you're looking like. And so it gets a little bit weird. And the Boozman-Feller condition is a little bit important as well, because in other words, you'll have the fat Cantor set, but you can only take averages over points. You might dial it in, but the point X has to lie inside that dilated the fat Cantor set, or translate the homotheticity of the fat Cantor set you're looking at. So some very interesting technical issues that come up. A great question.
It seems to me that this is pretty much related with the Kakeya technology that has been developed for the Kakeya
Yes.
problem.
Yeah, it is. Yeah, and so a lot of times it is correct. And so the Kakeya would be, unless you're trying to have certain a lot of times the Kakeya you're looking at maximum operators based on tubes of a certain, so let's say there's a certain like directions you're allowed to work with and eccentricities. But yes, it's a very, very similar ideas. Yes.
Okay.
I've kind of stayed away from the full Kakeya problems because I really don't want to compete directly against Terry Tao and Nets Cats. I'm going to lose. I'm going to lose that battle, and so I'm. That's kind of like I will stay away from there.
Yeah. Okay. So any other question or comment? So
So
well,
again, I'll say I think you guys have a great colleague in Wilfredo. I always like enjoy seeing Wilfredo at conferences, and so he's a great representative for Roosevelt University. And so Wilfredo, I'm going to be seeing you in about 6 weeks, aren't I? Yes.
yeah, yeah, yeah. Okay. Thank you very much, Paul, for your
Thank
talk.
you. Thank you. Thank
And
you.
it was a pleasure to have you in here in our little colloquium.
Yes. Yes. Thank you. Thank you.
Take
Yes,
care.
thank you, Paul.
Bye-bye.
Goodbye. Okay.
Thank you.
Bye. I've got a student to talk to, so I'll let you go. Okay. Okay. Thanks. Okay. I need to get out of here, right? Okay. Thank you. Thank you.
Yeah, bye-bye.